Welcome back to another Regents Physics review. This is for electricity, free response from the 2022 June exam. I actually added in as well one question from the 2019 exam because there were only two electricity questions on last year's exam in the free response portion. I will say when that occurs, it should be the last question in the video. So let's move into our first example. All right, so example number 12 on your packet. This is the first example in the video. To charge a cell phone battery, 3.69 times 10 to the third coulombs of charge is moved through a potential difference of 3.7 volts. Calculate the maximum amount of electrical energy gained by the battery. Show all work, including the equation and substitution with units. In brackets there, it is 2 points. Meaning on the Regents, this would essentially be two questions. So the first point is going to be, again, the proper equation, substituting in with units. The second point is then, again, the actual answer. So since this is just a math question, we don't have to do anything conceptual with this. We just have to pick out what is given to us in the question, figure out what equation we have to use, then get our answer. So looking at the first part here, it says to charge a cell phone battery, 3.69 times 10 to the third coulombs of charge. So charge, if I look for this, everything in this question is telling me electricity, even says at the end calculating the electrical energy. So that means I'm going to go to the electricity portion of the reference table and look for charge. So I see there that charge is equal to Q. So on the reference table, I have here Q is then going to be equal to what I'm given here in the question is 3.69 times 10 to the third. Let me fix that 9. Times 10 to the third coulombs. All right, the next thing that I'm given here in the question is that I have a potential difference of 3.70 volts. Again, looking at the reference table, I look for a potential difference on the right side, and I see here that potential difference is going to be V. So I have here that V is then equal to 3.70 volts. So that unit is just V for this. So 3.70 volts. The last part here, I want to calculate the maximum amount of electrical energy gained by the battery. So I'm going to look for what it says that electrical energy is on the right side of the table again. It's a little bit difficult to find because it is in parentheses. So in parentheses next to work, it says electrical energy. So the work done here is the same thing as my electrical energy. That is going to be W. That's what I'm calculating for. So that is going to be my unknown or my question mark. All right, so now we got to figure out an equation that goes with these three variables. So I'm going to look on the left side here at all my equations in the electricity portion of the reference table and find one that involves work, charge, and potential difference. If I look at the third equation from the top, I see here that V equals W over Q. So this is the equation I am going to end up using. All right, so what I'd like to do here first is solve for W algebraically so that it's easier to just plug in with units and do it then in one step versus having to do multiple steps with all the units written out. So I want to get W by itself on one side of the equation. It is currently being divided by my charge Q. So in order to get rid of Q on the right side and then move it to the left, I'm going to multiply it on both sides of the equation because the opposite of division is multiplication. So multiply Q on both sides. This will cancel it out on the right side and give me on the left here V times Q is then equal to my work or electrical energy. So now we can plug in our numbers with units and end up with our answer by plugging it into the calculator. So I have here V is 3.7 volts times my charge, which is 3.69 times 10 to the third coulombs. This is then equal to my work or electrical energy gained. So now I'm just going to plug this into the calculator. This all here is my first point. Now I just plug it in and get my answer, and that will be my second point. So 3.7 times 3.69 times 10 to the third. And I'm going to end up with an answer of 13,653 joules. So W is going to be equal to 13,653 joules. And that's my second point. My first point was everything running out the equation and substituting in with units. So let's move into our next example. So example number 13 in your packet. The diagram below represents an electrical circuit consisting of a 110 ohm resistor and a 220 ohm resistor connected to a source of potential difference. All right, so this is a multi-part question. This would be a few different questions on the Regents. So this is going to be done in multiple slides. What I'm going to do here on the first slide is part A, because I want to get into the equivalent resistance equation a little bit. And I'll do parts B and C on the next slide, and that will be shown in the chapters of the video. So the first thing you want to see with any of the circuit questions, especially when they give you a diagram, is what type of circuit it is, and also make your verb chart based on this as well. And that's just based on the amount of resistors. It doesn't change for the type of circuit. So what I have here, I'm looking at this circuit, and I'm looking at the two resistors here. That's going to tell me whether it's a parallel or a series circuit. And I can see here, if the current were to flow, it's going to have multiple branches to flow, and the resistors are parallel to one another. So that's going to tell me that this is a parallel circuit. So then on the reference table, I can use my parallel circuit rules. This tells me what happens to the current throughout the circuit, the potential difference throughout the circuit, and how to find the equivalent resistance. So now I can start filling in my verb chart. So the first thing I can see here is they give me a source of potential difference, otherwise known as a battery, a 6-volt battery. So I can plug this into my verb chart in the potential difference portion. I can see here that's the total potential difference in the circuit is based on my battery. So this is 6 volts. I can also see here, based on my rules, that the total potential difference is equal to the potential difference at R1, equal to the potential difference at resistor 2, and so on. So I can plug in 6 volts for the rest of my verb chart. All right, current I. If I look at the question and everything else, I do not have anything for current yet, so I can't really plug this in at all. R, I have my two resistors. The first one I see here, just going reading left to right, is the 110 ohm resistor. So I'm going to put that into my verb chart under R1. And then R2 is the 220 ohm resistor. They don't give me anything else here in the problem or in any of the parts of the problem, so I can't plug in anything else for the rest of the table as of now. So in part A, we want to find the equivalent resistance of the circuit. So look on the reference table. You're given an equation for this. It says that 1 over Req is equal to 1 over R1, so 1 over Req. Again, Req on the reference table tells me this is equivalent resistance. This is going to be equal to 1 over R1 plus 1 over R2, and then etc., but only have 2 resistors here. But you don't really have it equal to REQ. There's a different way I tell you guys to write this in class. I'm going to show you where this comes from. So since I have 1 over REQ on the left side of the equation, I kind of want to solve for REQ here. So the first thing I want to do for this is, since REQ is on the bottom and I wanted to get it on the numerator, not in the denominator, it's being divided by 1 in this situation, so I can multiply it on both sides. So 1 times REQ. On the top, this will cancel this out, and it'll move it to the right side of the equation. So I have here that 1 is equal to 1 over R1 plus 1 over R2 times REQ. Alright, in order to get REQ by itself, it's being multiplied by 1 over R1 plus 1 over R2, so I should divide it on both sides of the equation. So 1 over R1 plus 1 over R2. This will cancel out on the right side. On the left side, it will give me 1 over R1 plus 1 over R2, 1 over all of that. So moving forward with this, I have REQ is equal to 1 all over 1 over R1 plus 1 over R2. An easier way to write this out, which is the way I tell you guys to write it in class, is my equivalent resistance, REQ, is equal to 1 over R1 plus 1 over R2 to the negative first power. So now I can plug in with units and get my answer. So I have here 1 over REQ is going to be equal to 1 over, remember your parentheses, 1 over 110 ohms plus 1 over 220 ohms, all raised to the negative first power. When you do this, just plug it into your calculator, 1 over 110, 1 over 220, add them together, and then whatever the answer is inside the parenthesis, don't forget to then to the negative first. So I'll show you this step here, so there's no confusion with this. So REQ is going to be equal to, so plug this into your calculator here. So 1 over 110, then 1 divided by 220. Just add those two numbers together, and you should get around 0.0136. So 0.0136, this is ohms, all raised to the negative first power. So what you want to do here is just plug this into your calculator, and you should see somewhere on there x to the negative first. So you can just do answer to the negative first power here. And you should get your answer here. So you should get the equivalent resistance, REQ, is going to be equal to around 73.3, and don't forget your units as ohms. So with this here, your 1 point would be just writing out, you can write it out straight away as REQ equals 1 over R1 plus 1 over R2 to the negative first, and then plug in. And your second point is just getting the proper answer. REQ equals 73.3 ohms. Other like mistakes I see with this is just adding together the fractions improperly. You can't just do 1 over 130 based on this. That's improper. That's an improper way to add fractions. I would not recommend trying to find the find a common denominator for this. I would just recommend plugging these two into the calculator, whatever it is, 1 over that. just adding the decimals together and then doing it to the negative first to get your answer here. My equivalent resistance 73.3 ohms, and I can put this then into my verb chart. So 73.3 ohms. There we go. All right, so let's move into parts B and C. We're going to find the total current and compare power from one resistor to the other. All right, so moving into parts B and C here, we have here in part B, calculate the total current in the circuit. Again, show all work, including the equation and substitution with units. And in part C, we're going to compare the power dissipated by the 110 ohm resistor to the power dissipated by the 220 ohm resistor. All right, so let me fill out what I had in my verb chart from part A. So again, my voltage is the same throughout the circuit. So my total voltage is 6 volts, is the same thing at each of my resistors. I also have here my resistors, the 110 ohm resistor, the 220 ohm resistor, which is R2, and my equivalent resistance, which I found in part A, was 73.3 ohms. All right, this is where the verb chart is going to really come in handy because I want to calculate the total current within the circuit. So I look at the verb chart, the total current is going to correspond with my equivalent resistance row here. So within my equivalent resistance row, I have the voltage 6 volts and I have my resistance to 73.3 ohms. So start off here with part B. I'm going to look for an equation that's going to involve V, I, and R because I want to find my current. So I have here V, voltage, that is 6 volts, so I know that. I have resistance, which is 73.3 ohms. And I want to find current I. That's my unknown. So with this, I'm going to look for an equation, like I just said, that involves V, R, and I. If I look at the left side, my bad, of the electricity table, or electricity portion of the reference table, I can find here an equation that is R equals V over I. That is Ohm's law. So we have here R is equal to V over I. All right, so like we've been doing, what we're going to do here first is solve for I algebraically and then plug into the equation. So what I have here, R equals V over I. I want to get I by itself on one side of the equation. It's currently being divided by V. So what I'm going to do with this is multiply it on both sides of the equation because that's the opposite of division. So we have here on the right side, multiplied by I, that will cancel out. On the left, I have I times R, so I have IR is equal to V. What I'm going to do with this, since I have I multiplied to R, I want to get rid of R, so doing that, the opposite of multiplication is going to be division. So we divide this out from both sides of the equation, and I should have here now that I is equal to V over R. So move that up here actually. All right, so now with this, my current is equal to my potential difference over my resistance. Now I can plug in and I'll get my first point here, or actually the point can also come from just writing out these values up top, but really you should plug in with units. That is going to show you know what you're doing with everything. It's just better to go with this as well. So let's plug in with the units and get our first point. So we have here the current is equal to potential difference. which is going to be my 6 volts, over my resistance, which is 73.3 ohms. All right, so that's my first point there for this 2-point question on the Regents. My second point now is going to be getting my answer. So plug this into your calculator. You're going to do 6 divided by 73.3, 6 volts divided by 73.3 ohms. You will get out of this current, I, is equal to 0.0818. So let's round off to 2. And then my unit for current is going to be amperes A. So if you do not know what the unit for current is, it should show up somewhere on the test, probably in the multiple choice section. So if you do not memorize it for some reason, it probably should show up there. But if it doesn't, try your best to memorize it before test day, because it's not something that shows up on the reference table before then. So we can square this off here. That is my answer, and that will give me my second point on part B, or that would be count as 2 questions on the Regents. So now part C. We're going to compare the power dissipated by the 110 ohm resistor to the power dissipated by the 220 ohm resistor. So again, my VERP chart is going to come in handy here, and I'll fill out the current as well in here. So 0.082 amperes. My VERP chart will come in handy here because I really had to do some math here and then just show the comparison between the 2 resistors. So for each of my resistors on the VERP chart, if I want to find power, I'm looking for an equation that involves what I have here. So I have the voltage V for both of them. It's 6 volts, and I have my resistance. So if I'm looking at the reference table, so let's write this out here. I have voltage V, that's 6 volts. R1 is 110 ohms, and then R2 is 220 ohms. If you look at the reference table, there's an equation that involves V and R, and is going to give me power. Let's look at all my power equations. At the very right side of that, I'm going to have V squared over R. So the equation I can use to do this comparison is V squared over R. So I'm just going to plug this in for both of them, get the power, and show which one is going to be greater. So first, doing R1, which is my 110 ohm resistor, I'm going to find the power, and I'm going to plug in. So I have here 6 volts raised to the second power over 110 ohms. The other one I'm going to do here is 6 volts raised to the second power over 220 ohms. All right, so just plug it into your calculator. I'm not going to show all the work for this because it's just going to be 6 squared over 110 and 6 squared over 220. So 6 raised to the second is 36 divided by 110. So I'm going to get here that P1. So P1, this should be P2 because of how I've denoted the resistors. P1 is going to be 0.33, and the unit for that is watts, though it doesn't really matter for this situation. And then P2, plug this into the calculator again. So let's do 36 divided by 220. And I should get here that P2 is just about 0.16 watts. So if I look at this, it's pretty clear that my power generated by the 110 ohm resistor is greater than the power generated by the 220 ohm resistor, or dissipated. So I could just say here the 110 ohm resistor dissipates more power, or dissipated, more power than the 220 ohm resistor. then the 220 ohm resistor. Could have even just shown here 110 greater than 220, but writing out is probably your best way to go here. Actually writing out the 110 ohm resistor dissipated more power. Let me make that sure that's an A here. Dissipated more power than the 220 ohm resistor. All right, so let's move into our last example. That example is going to be from the 2019 Regents. All right, so again, this example is from the 2019 Regents. I decided to throw this in here because we had seen it before and it seemed to be a question that a lot of people struggled with. So let's go through this because it's a little bit of a combination between stuff earlier in the year and electricity. So again, this is number 14 in your packet, number 3 in this video. And I will do this in multiple slides and show that as well in the chapters of the video once more. So we have here the diagram shows a negatively charged oil drop that is suspended motionless between two oppositely charged parallel horizontal plates. The electric field strength between the charged plates is 4.0 times 10 to the 4th newtons per coulomb. The 1.96 times 10 to the negative 15th kilogram oil drop is being acted upon by gravitational force Fg and an electrical force Fe. So part A, and I'll probably do part E because they go hand in hand here on this slide and do part C on the next. Part A, calculate the magnitude of the gravitational force Fg acting on the oil drop. Show all work, including the equation and substitution with units. All right, so let's look here at what we're given in the question that could end up giving us the gravitational force. So that is Fg, that's what we're looking for. So let me put this down here first. Fg, that's my question mark. All right, in the prompt for the question, it says here we have a negatively charged particle. It's between two horizontal plates. It says what the electric field strength is. That's not really going to help us to find our force of gravity. But it does say we have a 1.96 times 10 to the negative 15th kilogram oil drop. All right, so if for some reason you forgot that kilograms is the unit for mass, they give it to you on the reference table on the front page because there's a few times where it says mass of something. So you have mass of Earth, mass of the moon, protons, electrons, and neutrons as well. And it gives you that the unit there is kg, which is kilograms. So that means that there's 1.96 times 10 to the negative 15th kilograms is my mass. What is mass on the reference table? It is not actually going to end up being in electricity. So force of gravity, going back to earlier in the year, where is that on the reference table? That's going to be in mechanics. So you either go back to mechanics for the first part of this question, because force of gravity doesn't show up anywhere else. So go all the way back to mechanics, the back page of the reference table, find that mass is going to be m. And for this question, that is going to be equal to 1.96 times 10 to the negative 15th. Let me fix that. Times 10 to the negative 15th kilograms. All right, what else do we need in order to find the force of gravity? There are two equations for this. You either have universal gravitation or you have G equals Fg over m, or like how I like to write it, Fg equals mg. You could do this with universal gravitation, but it's a little bit longer and a little bit more annoying, even though it actually would work if you use the mass of Earth. But it's a lot easier to use the gravitational field strength equation. And the last part of the equation that we do not have here is going to be G, which of course is going to be equal to, tells me on the front page of the reference table, 9.81 meters per second squared. So the equation that again involves all of these is G equals Fg over m, or just writing it a little bit simpler, is Fg equals mg. All right, so now we can plug in to the equation here and figure out our answer. So we have here Fg is equal to, the mass is going to be 1.96 times 10 to the negative 15th kilograms multiplied by g, which is 9.81 meters per second squared. All right, so now let's plug this into your calculator, and you're going to end up with your answer here. So 1.96 times 10 to the negative 15th, multiply this by 9.81, and you're going to end up with your force due to gravity here as Fg is equal to 1.92 times 10 to the negative 14th newtons. All right, so my next part here is going to be part B, and this is going to be fairly quick. So let me section this off here. Oops. All right, so part B has to do with Newton's second law. So I'm actually going to do it next to the free body diagram up here. So I'll put B up here. So Newton's second law, what does it state? It states that F net, or you can just recognize it based on the diagram as well. So F net equals ma, or the sum of all forces, the better way to write it, equals ma. All right, so it tells me in part B that determine the magnitude of the upward electrical force, Fe, acting on the oil drop suspended motionless. So if an object is motionless, what is that going to mean for my acceleration? If it is motionless, my acceleration should be 0. So there's two situations where my acceleration is 0 in mechanics. When you have Newton's second law, it's either you have a constant velocity or it's just not moving at all. This is the easier version of the two. So this acceleration is going to be 0. So look at the forces that are present on this free body diagram. It's going to be equal to 0. So going upwards, I have the force of electricity. That's Fe. Going downwards, I have the force of gravity. That's Fg. Should all be equal to 0. So doing a little bit of algebra, I have here that Fe is equal to Fg. So that means that Fe is going to be equal to the Fg I got below, which is 1.92 times 10 to the negative 14th newtons. So let me fix that 0 there. So my force of electricity is going to be equal to my force of gravity, and that's just based on Newton's second law on my free body diagram, and they give me the free body diagram in the diagram here, so I don't even have to create that. So that makes it a little bit easier for me when making Newton's second law here. So we're going to then use this in part C, and I'll show that in a second. So keep in mind, and I'll write down on the next page, that Fe is equal to 1.92 times 10 to the negative 14th newtons. So let's move into part C of the question. All right, so part C, we want to calculate the net electric charge of the oil drop in coulombs. So again, what is charge? So now we're going back to electricity because it's saying electric charge, oil drop in coulombs. That means I'm going to go back to the electricity portion of the reference table. So in the electricity portion of the reference table, once more, charge is what we're calculating for. That is a question mark. That's what we're looking for. What am I given in the question? Well, what we found in part C, part B, my bad, that can help us is our force of electricity. So we found this in part B. Fe is 1.92 times 10 to the negative 14th newtons. So that might help us here. What we're also given here in the question, we are given that we have an electric field strength between the charged plates, 4.0 times 10 to the 4th newtons per coulomb. So electric field strength again, if I go to the reference table, that is going to be E, so big E, is going to be equal to 4.0 times 10 to the 4th, and that is newtons per coulomb. So let's look for an equation on the reference table that involves all three of these variables. If we look on the left side, the second equation from the top, electric field strength equals Fe over Q. Q is what I am looking for, so I can use that equation to get my answer. So I have here that E is equal to Fe, my electrostatic force, over Q. So again, what I'm going to do here is solve for Q first, because I have to show our work, including the equation and substitution with units. So I'm going to solve for Q first, then plug in with units. So again, I want Q by itself in the numerator, essentially. So it's being currently divided by the force of electricity. I'm going to do the opposite of division and multiply Q on both sides of the equation. On the right side, it will cancel out. On the left, I'll have electric field strength times charge Q is equal to Fe. I wanted to get charge by itself. It's currently being multiplied by electric field strength. So in order to detach it from charge, I'm going to divide it from both sides of the equation. It will cancel out over here. And I'm going to be left with charge is equal to the electrostatic force over my electric field strength. So now we're just going to plug in everything from what we've been given, what our givens were on the left side of the page here, and get our answer. So remember to have it with units. So charge is equal to Fe, so that's 1.92 times 10 to the negative 14th newtons, all over my electric field strength, which is 4.0 times 10 to the 4th newtons per coulomb. So just plugging this into your calculator now. Again, that's my 1 point I plugged in now with units. Now let's get the second point and get the answer with units. So 1.92 times 10 to the negative 14th. That is then going to be divided by 4.0 times 10 to the 4th. And we should end up with our charge here, Q. Let me move over this actually so I have more room. Should end up here with our charge Q. That is going to be equal to 4.8 times 10 to the negative 19th. And this will be in coulombs C. So that is going to be my final answer here, 4.8 times 10 to the negative 19th. And don't forget your unit there, coulombs. All right, so I hope this review was helpful. Good luck in studying for the Regents, and see you guys in class.